Right, good morning everyone. Right, so as you can see, that's the norm for the day. It's the wave energy and wave devices. So by the end of today, probably you may feel why we need this and how we need this. Are you able to spend the euro to light the bulb with the wave energy? So that's the norm for today. And before I start, any questions or anything which you want me to address? Happy days. That's good. So I received a question from one of your friends again, who is doing the class. How are we going to frame the questions? Again, it's all boiled down to exams these days because it's just 1 month away, right? So the questions will be asked mostly on the slides, the notes which I have presented, and also I will be also giving a brief recipe of the previous lectures in the video form as well, sooner or later. And so we should be able to do well. I don't see any problem. And the sample questions which I provided are helpful questions. Some of them may not be covered, some of them may have been covered. So whatever I covered, within the boundaries only the questions will be there. But it will be slightly on and off maybe, but you need to read the textbooks as well apart from the notes. Is that okay? Right. Okay, this time I have to do myself. Okay. So that's a norm for the day and the norm for all our classes. Remember to turn off your mobile. Right. What do we have the recipe for the day? The menu for the day is waves, wave energy in the ocean, an introduction, different types of waves and its effects, harnessing the wave energy and principles possibly, and the state of Jesus, why it's coming again? Hope it works well. State of art technologies, economics, and future prospects. So that's what I will be covering today. And if I get some more time, I would like to also touch geothermal energy as well. If I'm able to cover all these things, and if I have another half an hour left, so I will be covering geothermal. Is it okay? So, what do you know about waves and wave energy? The introduction, the different types of waves. What is different types of waves? Anyone has any? How many of you are doing wave energy assignments? Anyone here? No? Okay. How many Irishmen here? Yeah, I think 20. 20 of Irishmen, okay. You will be in for a surprise now. Some of the data. For the first time, I'm going to introduce an Irish version. Okay? Competing with the French guys on the top of the table here. Okay, it's getting a bit warmer. Alright, let's go. So it is estimated that if about 0.2% of the ocean's untapped energy could be harnessed, and it could provide sufficient for the entire world. About 0.2% energy, and you know what is tidal and water currents, how the temperature gradients is going to make a big difference. Atmospheric effects, we have been discussing that, and salinity, and also the wave power generations and different sort of wave powers. Okay, compared to other renewables, wave power has advantages, higher availability. We can't disagree, right? Higher availability. So water is there everywhere, ocean, seas. Okay, and you know why UK doesn't come to Ireland, because the border is huge. So more predictable and forecastable, up to 10 hours forecast time, low V-shed impact. At present, wave energy is estimated to be 20 to 30 cents per kilowatt, so it is expensive. Why it is expensive? Sorry? Yeah, go ahead, sorry.
Technology and materials that we use for the city.
Technology of materials?
Technology and materials that we use.
Yes and no.
You've got to build something standard for waves.
Sorry?
You've got to build something standard for waves. So you've got to over-engineer things. And also, what was the case also the cost of getting the energy back from the device back to land.
It's more.
It's a huge point.
Then compared to how much you get out of it. Any thoughts? At present, it is stored coal and wind is about 4 to 9 cents per kilowatt. Why is that wave energy is more? And having said that, why it is less exploited when compared to the other energy? Because we all know what water takes majority bulk of our earth, right? So why? Any ideas? Come on, don't Google it. I'm just joking. Any ideas? Why? Why at present the wave energy is estimated 20 to 30 cents per kilowatt? Cool, okay. As Paul said, technological challenges are there and the capital investments. So, but how many countries are participating in wave energy when compared to the other countries? Because so everyone is going on solar. Last week I showed you the map of renewable energies, right? Which are all the countries are keen in wave, hydro and solar. But why the countries are not investing time on wave?
Good and not.
Sorry?
Good and not.
Good?
Too much land lock.
Too much landlock? Possibly yes and no. Yes and no. So tell me which country is pioneering in wave so far? France? UK?
Denmark, Portugal.
He's getting closer. Denmark is there. Is on the right on the table. Close to top. Yeah, he's right. Norway. Norway is the one that's pioneering the wave a lot. Norway and Denmark. And then Paul is right, UK is falling in the table as well. So as you can see that even though US is investing a lot of money and time on renewable energies, but most of the renewable energy pioneered by either by Germany in case of solar and also wind, and now Norway and some of France and UK. So the Europe is really heavily invested on renewable energies, and they've also coming into the picture. And as we said, there are huge technical challenges in also understanding where to get and when to get the maximum peak energy and peak power, how the storage. The difficulty is in the storage, how we are going to store the energy. And one of the major energy is countries like Ireland as well, there's wind and wave, because solar you won't get much, if you have to invest. So, but whereas when the dam conditions, definitely wind wave energy will help you start investing on time. That's why the spirit of Ireland, did I mention about that, right? Quite a few times. They do take care of hydro and wind. So I would advise if somebody is doing something on wave related projects or assignments, it is better for you to refer Spirit of Ireland and Sustainable Energy Ireland website. So it's a good website. So, and I'm planning to upload some more documents for your references at some stage. Probably if I can get some time today or tomorrow, I will do that. There are quite a few good documents which we can do that, okay? So the prediction is wave power is about 50 years behind. That's quite a lot, isn't it? 50 years behind. So I'm not sure whether we will see in our century, in our decade, okay? So 50 years behind wind, but it's predicted that wave power can catch up quickly. But it's a bit of overstatement from myself because I'm still not confident. But if other can prove me wrong, the engineering guys and the other policy makers, because then probably there may be some game in it. Okay, this is the global wave energy distribution. Okay, so I took this thing from the reference. Where is the reference? Oh. So I took it from the IEA, International Energy Association document, which is 2010 version. Okay, so the global energy distribution, as you can see that as forms of renewable wave energy is unevenly distributed over the globe, right? It is unevenly distributed. Do you know why it is unevenly distributed?
Investments.
Winds, that's correct.
Currents.
From the graph. You can even take it from here. What are all these numbers? Indicate.
Angle.
What angle? Yeah, exactly. What angle? Okay, they are latitudes. Okay, the most appropriate latitudes to get higher wind and higher wave is between 30 and 60 degrees, or slightly higher. So we are somewhere here, right? Ireland, 60 and 70. So Ireland is somewhere, and the entire European belt is also very nicely placed to get more the things on both sides of the hemisphere. Sorry?
Sweden and Denmark.
Yeah, exactly. Yeah, that's what I said. So Sweden, Denmark, and Norwegian countries. So those countries, they will be hugely beneficial, including Ireland. And you won't believe, in 2020, by 2020, Ireland is thinking of getting up 2.5 to 6 kilowatt or something like that from megawatt from wave energy for the commercial use. That is their roadmap in 2020, and probably they may reach. I'm not sure. So that's the reason. So as form of more renewable energies, wave energy is unevenly distributed over the globe. Increased wave activity is found between 30 and 60 degree latitudes. So if you see, India is not heavily placed; it's around 10 degrees. And then see, that is one of the disadvantage of India. And what is this country here? I don't know. Japan, yeah. I can't say Japan is not really placed. They are. You will see in my slides. They are the first few to make wave energy devices. Probably, yeah, they can make the devices and sell. So South American countries, Africans are also okay, moderately placed. So there are plenty of. It is, although we say that wave energy is important, but if you the research development is all taking place in form of clusters. Okay, whereas solar is carried by everyone in the globe. So this is the reason why, right? And it may even answer your question why this cost is very high, because some of the people are not interested because they don't get much wind on that side to get more current, and they don't want to invest more money by the return on investment is less. All right, but if they are clever enough, they can develop the technology. They can develop. They don't want to harness. They can develop, and then they can be a wholesale producer of the technology. That's another part. They can license the technology to any other country. So that's a completely different ball game on the economics and technology transfer. Okay. So.
There's big installation on.
Sorry.
There's big installation on Canada as well.
Yeah, big installation in Canada as well. Yeah, that's true. That's true. And Canada is also using a technology called what is it called? Bob thing. Sorry? Wave bob. They use wave bob and oscillators as well, very heavily. Okay, so yeah, Canada and good on Niagara. Next one you'll come to Niagara as well. Yeah. Okay, so this is European wave distribution. So yeah, that's where I took it from International Energy Association. So it estimates that there is a potential. That is a term. Potential, but I'm not sure what they do. Potential to generate 1500 terawatt hour per year. That is 10% of the global demand from wave power. Again, you can see that that's Ireland again and UK. They're all nicely placed. You can see that no commercial waveforms yet exist, but there are several beta installments. Okay, they are working in pockets. the commercialization is far from the reach because of the very high cost and returns. Okay, right. The Irish context again, estimated power of Atlantic coastline is about 40 kilowatt per meter exposed. So you can clearly see that Ireland is nicely placed between North Sea and the Irish Sea as well. So you can see that there are about 40 km per hour and 250 km westerly. So you get huge waves patterns in which part of Ireland? Which part of Ireland do you get? Which part? Which county? Okay. There is an Irish guy who made a wave device. Okay? He's not which county. Any idea? He's really famous guy. Wave device, wave energy device. He's one of the earliest guys to make a wave energy device. Okay. Huh?
Is it a hard one?
He can't even believe that he's an Irish guy. Yes, he is. Which county? No idea, guys. Good, no problem. We'll carry on. Keep the suspense for some more time. Alright, okay. So, the highest energy points is from Northwest Mayo, County Mayo, Western Galway, West Cork and Kerry. So there are lots of marine farms are also there in Galway, right? Galway Bay. Right? So if you are successful in harnessing the ocean energy, it could be used for different purposes as well. For powering even solar cells, I'm not sure. And also for anti-biofouling. There are plenty of things which we can do to get rid of. So that's why the people are working on West Cork, Kerry and Galway, in those areas to harness more current. And the government has invested in these counties a lot over the years. Okay? The trade-off between the available energy, which increases with distance from land, and practicalities of like any other renewable energy. It's applied to every renewable energy. Right? The storage and transmission is critical, and similarly, wave energy is no exemption. Again, the practicalities of harnessing and connecting to grid is another challenge. How are we going to do that? So probably we'll be dealing more of storage in the next class. I promise that I'll give the flavor of storage next class. Okay? So we will see what challenges are there. Okay? And it's again reference from Cambridge thing. Okay? Wave energy. Right, guys. The ball is on your court. Is it renewable? If so renewable, how it is produced? Sorry? Wave energy, the wave, you can say how waves are produced, whatever it is. How wave energy is produced? Is it renewable energy? That's the first question. So everyone agree to disagree or agree to agree? Is wave energy renewable? That's the first question, right? How it is produced? Sorry? I'll go by the tape. Since we have only a few people today.
Probably affecting the moon, I believe.
Sorry?
And the waves affected the gravity of the moon, gravitational.
Moon's gravity?
Similar to tidal.
Similar to tidal? Okay. Do you have anything to say? No problem. Wind? Wind? Wind and air pressure, differential pressure? Okay. Wind? Just wind, that's it. Okay, wind is the wind current.
Ocean currents?
No? No? What do you say? You say ocean currents?
Yeah.
How ocean currents are produced? That's a question. That's another question. That will answer the question again.
Difference in temperature?
That's two questions. There are two key words scale between those two guys. Difference in pressure difference in temperature, right? Right? And somebody said moon, and somebody said wind. Right? So, if you all put together in a package, that's how it's effectively produced. And the current which you get from the first line, that's the current you generate from here. Right? Is it okay? Right. Wave represent clean and renewable energy source came into being by conversion of wind energy when wind blows along the sea level. Right. I know that I have been giving you some simple examples over and over again from the class. I want you guys to give me a simple example of wave energy. Very simple example, which you can think of in a normal day to day. Normal day to day. I can see that you can easily say from your table itself. Some of them having some examples in their table. Few of them. The wave. Sorry? Probably I am stupid, okay. I'm looking for some very simple answer. Very simple logical answer. Simple logical answer. How waves are generated. Very simple logical answer, not big. Probably I am stupid, but I'm asking you this question. Sorry? Movement of what? Movement is right.
The wind on the water.
Exactly, that's what I'm looking for. Movement of wind blowing on the water. You have water on the table, right? You just blow, but there is a huge physics and technology behind it, right? The force comes to the picture. The oscillations come to the picture. And the oscillations, even if you drop water on the ocean, right? Or you are going into, say, rain or whatever it is. So you throw water on it. You throw a stone on it, you get ripples, right? So what happens? And again, if the ripples are getting more and more pressure induced, it becomes wave. Right? So the thing is, the blowing needs force. The force is again goes back to Newton's. Right? Now the question is, how much effort is needed to get that amount of wave? Right? Is a critical point. That is why the trade-off comes before we are talking about how much energy which we need to invest to get the returns. Right? Is very, very less. So you spend more energy, but the return on investment is less. That is one of the reasons why it is not still analyzed. So you grow water, the technology has to be reached publicly easily, societal. That is not there. Okay, the wave process. Okay, next. The wind originating from. This is one of the things which we are missing today. I mentioned several times in our lecture, solar is the key for all, is the mother of all energies. We agreed, right? In a few classes. This is also originated from solar. So wind originating from solar because our friend said sun heating, because of sun heating produces differential pressures, high pressure and low pressure, differential temperatures. So these cause the wind to flow. Okay, so you can see that this is ocean, right? And you can see that the wind generates an area may be bounded by coastal lines by extent of wind. So you push, because of the differential pressure, the wind pushes the water and the ripples to chop to the ends of the wave. So you started spreading the wave in a conical fashion, and also we start with conical and then goes to spherical, and the ripples will spread according to the differential pressure and wave direction. And then there is a term there again. There are three key terms. This is swelling. Why the swell? This is called swelling. You can see towards the end. So when you drop a stone on the ocean, the wave spreads, the ripple spreads. Towards the end it spreads. If you see the interference pattern, the waves are interfering, right, to each other. If you see the interference pattern, at one stage, the time gap will be very less. Other stages, the time lag will be more. So depending on that region is called swelling region. Okay, I'll get to more about the details. What is swelling? Why tsunami is caused? Can anyone tell? Why tsunami? What is the reason? From the wave. Don't go too much details of earth and all those things. Okay, from the wave phenomena, you can tell 5 tsunamis. Depth of water. Okay, I mentioned something on the time. Can you say with respect to time? Never mind, don't worry. We'll go through it. Okay, we'll go through this exercise. No problem at all. Okay, that's fine. So uneven heating of the Earth's surface. So I want to cover your point as well. Uneven heating of Earth's surface is caused wind, and wind eventually drives the waves, and waves are concentrated from the solar energy. So everything boils down to sun, right? So this I took it from this diagram is adapted from electric power, EPRI, electric power research institute. Okay, that's not mine. Right, generating a wave. So when the wind blows across the smooth water, when wind blows across the smooth water surface, air particles from the wind grab the water molecules. They touch. The force of friction between the air and water, when wind blows across the smooth water surface, air particles from the wind grab the water molecules, they touch. Right? You blow something on the water, that's what is happening. Air particles will touch, and then it grabs, and then they form a layer. The force of friction between the air and water, the force of friction between the air and the water stretches the water surface, resulting in the ripples. And that ripples is called capillary waves. Okay? And where L is less than few centimeters. So L is the length between the different waves. So as the wind continues to blow, the waves goes bigger and bigger. And we call these waves gravity waves because their potential energy is due to the force of gravity. So somebody mentioned about potential energy here today. So they are also right. Okay. So all the things we need to do is, as we said, we all know everything. I think the guys here all really know everything. All you need is you pick points from different area and start to marry each other, then merge each other, then you will get a really good story. You know everything, in fact. So as the wind continues to blow, that's what I said. You know what is how it is produced by differential pressure, differential temperature, potential energy, and the solar. So you put everything together, you get there. Okay, what is this? What does this picture tells you? This is rough waves, differential waves. One is higher amplitude, other is lower amplitude, right? It's rough, everywhere it's rough. So if you are getting these kind of rough patterns, rough wind patterns, how are you going to harness the energy? How are you going to store the energy? It's how your technology is going to adapt. That's a challenge, right? Isn't it? That's a challenge. So that's what here. See, the wave profile of the sea varies. So the superposition of the wave with many different characteristics generated in very far away places. So you got this, you go from the bottom to top. You go from sinusoidal waves, and then the periods is getting increased, and then you get a huge waves. Right? So this is due to differential pressure. Okay, if I go back here, okay, I'll go back here again. So these are all due to what? What is causing these kind of differential wave patterns? Bit of physics involved. I'll introduce you the same thing in the next slides. Interference, yeah. Interference in the phase. So one wave will be out of phase, other wave will be in phase. If both waves are emerging, then you will get either destructive waves or constructive waves, right? Are you true? Are you with me? Yeah, that's what is happening clearly. And you have to find a device which detects the differential pressure, because it causes the differential pressure in the sea level. So how we are going to make a pressure sensor with a differential gradient? So there are other challenges, which is sustainability. We'll talk about basics of now wave energy, right? So, Jesus, no. I think I'm in a hurry. Somebody is chasing me a lot. Okay. The basics of wave energy, right? Each surface, because if you have a very smooth surface, I mean smooth water is there, and you start blowing, the surface will oscillate, right? Or like I'm trying a string here, and it's very smooth, so I tap the string, so it oscillates very slowly, right? So that is what exactly the situation in which I want to give here. So each surface wave traces in form of a circle. So you can consider them as the pockets of circle, they are pockets of circle. So these circles, if you see, there is a reason, there is an arrow going all the arrows are pointing in clockwise direction. So this has a particular diameter, and that is called wave height. Okay, the surfaces waves in the open ocean propagate horizontally, carrying their energy. However, the water parcels, these are all called water parcels or water pockets, associated with the passing wave do not propagate. Rather, they move in a relatively small circles in place. So that's the basics of how wave propagation takes place. Okay, so what is wave propagation again? So what is one wavelength? We all know what is one wavelength, and one wave the time takes to propagate one wavelength. So from one point to the other point of the peak, that is one wavelength. We know that. And wavelength, again, wave speed is given by wavelength over time. L by T is Cp. Okay, that's very, very simple basic physics. Right. The question to answer which I have asked you guys about tsunami and the capillary waves. So this is what it is. The waves are classified or sorted in a spectrum according to their wave time periods. Right? So when tsunami happens, it's a destructive, right? The time period is more huge. So it takes, the wave hits a lot. Look at, if you see the period is more. So there are different types of waves. These waves are called capillary waves. With the time, what we are doing, like when you start thinking of blowing the water, right? With whatever it is, with the cup or a mug. So you have water and then you try to blow. Their time period is about less than 0.1 second. So they are called capillary waves. Okay. When the ocean swells, so ocean swells means the waves with slightly longer time period, it's about 15 seconds, that's ocean swell. So this is about 15 seconds. If you see that, the time period is always measured by the peak is full width half maximum. Okay, full width half maximum is nothing but, so you take the peak, okay, this is the peak, and then these take from the height to the valley, peak to the valley, and then the half of the peak to the valley is full width half maximum. Okay, so you measure the full width half maximum, and that will give you the time period 60 seconds. Whereas you can see from capillary wave is 0.1 seconds, whereas in tsunami it's about 20 minutes. It's quite a lot. The wave time period is 20 minutes. So that's why it is destructive. It carries more power in it. More power and force, exactly. Okay, because of differential pressure. So the amount of energy in particular wave classes is determined by typical wave height in each case and the time period. Anyone needs any clarification on this? Sorry? We can put wherever it is. It's in, where I put the height. I didn't put height measurements at all here. Oh, here, it's centimeters, sorry. That's in centimeters. Any questions? Okay, let's move on. Right, the waves, wind waves and swells. So the waves are generated by wind or wind waves. When the waves propagate outside their region of generation, they are called swells. And water is deep, of course, and the swells can travel at larger distances. So the swells can travel at larger distances than the water because of the differential pressure. For instance, the oceans almost without losing any energy. Right. How do ocean wave exist? We know that the force and the gravity we were mentioning. So we have a disturbing force and the restoring force. It's all like, again, going back to Newton's third law, force and the reactions and disturbing. So it's all, if you recollect your simple harmonic motion, it's pretty much the same. Okay. So the gravity restores the sea surface disturbance, most often caused by wind, towards flood ocean equilibrium. The overshoots, keeping the cycle going, in which the potential energy elevation is converted into kinetic energy of motions and back again. So these oscillations happening, right? These oscillations are happening because of differential energy as well. The energy is neither be created nor be destroyed, but transferred. That is what exactly happening. So from potential to kinetic here. So these oscillations, so you need to pick where you want to take, right? So bit of wave mechanics and equations. So wave particles moves in a circular orbit, decreasing in radius as depth. So these are all like in a deep oceans. So this is what is happening. So you have a waves, and these are all wave particles, which we saw in the first slide, which moves in a periodic manner. So if you draw a line or in a conical fashion, you will get this, and wave particles moves in a circular orbit, decreasing in radius as depth increases. The energy, so what happens is the energy, as I mentioned to you, the energy is transmitted from potential to kinetic. So we need to understand what is happening, right? So the energy is transmitted, not water is transmitted, energy is transmitted, and the wave speed phase. So we know why we get the destructive wave, why constructive wave. We saw that, right? We get rough waves and we get something smooth waves. So we need to know why and what is phase, in phase, and what is out of phase, how it is happening. So this is a simple equation to determine the wave speed is C is equal to G lambda by 2 pi. So using a typical wavelength of 100 meter wavelength, this gives a wave speed of about 12 meters per second or 25 meters per second. So this 100 meters per wave, 100 meter wavelength, say if it is in County Mayo or in Galway, is happening using a typical wave at 100 meter wavelength in County Mayo. This gives a wave speed of about 12 meters per second. Okay? So I'm not asking you to calculate. Don't worry. So wave power part. So we saw energy. Now power. So wave power propagation. So another bit of equation is the time period. To A, Z is equal to A sine mu. Mu is nothing but 2 pi by T. 2 pi x by T. X is the distance in the propagation. So x, this is, say for example, x, the wave moves from x plus delta x, from slowly carrying its energy from kinetic to kinetic potential. So what is happening here is energy in one wavelength per unit is given by 50% kinetic and 50% potential. Do you agree? Why it is 50% kinetic and 50% potential? Sinusoidal, right? It's happening at one phase and the other phase. The equilibrium.
It's like it's duty cycle.
Duty cycle. Yeah, exactly, it's like a duty cycle. So you take one phase and the other phase. So it's 50% kinetic and 50% potential. So this is the equation, is half rho g A square. We have seen this many times, right? Similar type of equations. So it is the same here, and the energy propagated with group velocity. So I'm not going to much into group velocity, what it is. So these are all the simple equations from the group velocity, and if you calculate for the power, and this is the equation for the power. So you don't need to heavily mark up these equations, just have a flavor. Okay? How do you measure the waves? So we know what is waves, we know what is wave energy, and how we calculate the power. Now, how do you measure the waves? The measurement void are used to record the wave parameters at different locations. So you take the buoys and you can start measuring. So I will tell you what is there inside as we progress. And such physical measurements have been performed during last few decades. A typical measurement lasts for about 20 minutes and is repeated every year, every 3 hours. So that will be talking about differential pressure, differential temperature parameters, and how the waves are getting affected. These are all like small capillary waves or swelling waves as well. So it's again back to Norway. So this is this measurement made in Norway. So right. So I introduced you the wave energy, what it is, and how we measure the different types of energies in it, and I also said about how do we measure the wave energy. So right, how do we compare? How do we compare with other energies? Wind, photovoltaic, solar photovoltaic, hydro, etc., etc. So wind. For example, wind, the power density is approximately 300 watt per square centimeter or square meters. The theoretical maximum of wind power is about 60%. I think we agree, right? We saw in the last class. 50 is it? Yeah, 50 or 60 watts. Typically to about 40 to 50%. And rural resource far from population, and it's expected to be in 4 to 9 cents per kilowatt. Whereas solar photovoltaic is approximately power density is about 150 watt per square centimeter, generally around 15% efficient, and it can be used for both urban and rural, 20 to 30 cents per kilowatt, and it's quickly falling down. Wave. The power density is approximately 30,000 watt per square centimeter. The theoretical maximum of wave power captures is 100%, although it's highly device dependent. For a point observer, like in single buoy, there is what you measure is a point observer, right? The measuring device, it's observing. So point observer, the maximum power capture is about 50%. The typical values is yet to be determined because it varies from coastal to coastal areas. So coastal, close to populations, 20 to 30 cents per kilowatt. So it's quite high. Okay. Difficulties. What are all the difficulties facing the wave power generation? Facing the wave power developments. Wave patterns are irregular. As we saw a few slides back, they are irregular. They are not regular patterns. Difficult to design devices. I said few minutes back. Difficult to design devices. Extract power efficiently over such a wide range of variables. So we have plenty of variables there. Difference in pressure, difference in temperature, and then difference in wave patterns. So you need to find a device. There's a huge difficulty there. And then probability of extreme gales or hurricanes. You need to expect for the unexpected. Right? It's not like solar where you have sun always, you will moderate temperatures. It's not. There is a huge disadvantage. So hurricanes needs to withstand the conditions where 100 times power density, which are they normally mismatched, will be there. Okay. The peak power. Okay, this is a slightly, what do you call? Probably we should concentrate on this maybe. Peak power normally available in deep water from open wells. Very difficult conditions construct to fix and maintain devices. So, but the peak power normally available in deep water from open wells. Very difficult conditions to construct fix and maintenance devices. Again, it's like coal mining, right? Somebody has to go inside and dig and start living their life for others. It is what exactly you need to go and live in water for maintenance, which is really painful, right? So that's again a hazard. So peak power normally available in deep water from open wells. So difficulties facing wave power again. The wave periods are typically low frequencies. Difficult to efficiently couple this slow irregular motions via electrical generators. So you need to generate the storage and then transmission. So it is difficult to store because of their low frequency. Many different devices, different types in public domain, which to choose. It's because of its irregularity. Because of its irregularity. Economy of scale is questionable. Peak power is generally only available from land and remote from dense populations. So it's available somewhere in the middle of nowhere. So how we are going to do this? What we are going to do this? That's a big question. Then capital cost, as we discussed, capital costs are very high due to the necessity to withstand harsh environments. Right? So are you guys agreeing to everything in this slide? Or you want to add some more in it? Okay. Silence. Take this agreement. Advantages of wave power. Right. So far I was scribbling about wave is so bad, guys. This is really happening there. So I have to give flavor of what is the advantages as well. So what are advantages? Large energy flux is available, predictability of wave conditions over a period of days, possibly, if we are lucky. We know when it's quiet, when will be quiet and windy, and maybe for that's why I said over a period of days, not for months. Okay, possibly you have, if you are able to generate more energy and store the energy, then possibly we can do something. And low environmental impact when compared to others, where wind you have to put on the land and the noise. Sorry.
You put the wind out of the sea as well.
Yeah, out of the sea as well, exactly. But people are, again, the same question, the transformation, maintenance, it's all coming into the picture, right? So, for that you can also use a combination of wind and the ocean. But if something like hurricane or tsunami comes, everything goes up, that's it. Okay, that's another issue. So, say again?
Plenty of storage then.
Yeah, plenty of storage is needed and transmission is needed. Okay, so low environmental impact with little visual impact. The visual impact is what we are talking about. The solar cells, it needs cells. It has again visual impact. People doesn't like, all those things will come. And then wind has another thing like wind-based whereas this has lower environmental visual impact. Since only small fraction of air power is extracted, impact of coastline is minimal. Chemical pollution is minimal, so you're not going to pollute anything. Or maybe yes and no, it's minimal. Minimal is again is a relative term. Okay, so no obvious problem for marine life. That is again an overstatement maybe. The load factor of energy supply from ocean waves matches the demand of electricity. Wave power is largest in winter when demand is increased. So probably we need to know how we are going to harvest at least the energy in winter. That's what probably the European scheme is also after. Okay, so the economies can be achieved by installing wave generators in groups and connecting to shore via a single submarine cable. That is what the global economy is moving towards. Global economy can be achieved by installing a wave generator in groups and connecting the shore winds via submarines. Okay, so submarines will have a lesser impact when compared to other. Okay, properties of deep water waves. Surface waves are sets of unbroken sine waves of irregular wavelength, phase and direction. The motion of any particle of the wave is circular. Surface form of the wave shows progression, but water particles have no net progression. These are all the conclusions which are getting from the previous slides. So water on the surface remains on the surface. The amplitudes of the wave water particle motion decreases exponentially with depth. We know that as you go much deeper and deeper, the amplitude will be lesser when compared to the shore. Okay, the amplitude of the wave is independent of wavelength C and T. The wave will break into white water when the slope of the surface exceeds 1 in 7 of the scale, the dissipating of the energy potential. Okay, what are the opportunities and challenges? I'll quickly go through. Pulse power, marine environment. Salt water is corrosive to mechanics and electronics, can be violent. Survival techniques still being researched. Slow speed, high thrust torque. Hydraulics can be maintenance and intensive. Interest in direct drive rotary. Again, it's all boiled down to how we are going to harness the wave using technologies. That is why we are talking about the turbines. So, from linear to rotary mechanism torques, about 5 mega Newton meter or more may be typical. Oscillating motion of the waves is stressful due to mechanical components. So, waves are oscillating, right? It has to periodically hit the surface. Again, more torque, more force, more restoring force is there. So, again, how we are going to harness those potential and kinetic energies with respect to the mechanically stable elements. That's a challenge. Interest in linear machines, although difficult economically to high power. Mooring can be complicated. Field maintenance, we saw that why field maintenance may be tricky, seasonal. Optimal control in a structured environment. Okay, cables mooring system. Can any marine life become entangled? Electromagnetic fields, again, there are already many undersea communications and power cables. With marine life will be attracted or repelled by these kind of communications. It's electromagnetic waves. So the electromagnetic waves are going. So we are talking about storage. We are talking about communications between one submarine to other submarine. How we are going to do by electromagnetic communication? Electromagnetic waves will be communicating. So if the electromagnetic waves are passing through, will there be any effects on the marine life? Fishes. Sensitive, exactly.
It's only a short distance.
But if you put all these in the series, right? So the idea of the current technology is to put a submarine, isolated submarines everywhere, and connect them into series. So you transform from one to another through communications. So that small thing will become bigger as well.
Also talks about emergency water and hydrogen,
Alright, that's a different story. That's hydrolysis.
and then public action.
I will come to that in the storage as well. That's where the storage issue will come. How we are going to store this. We can also pump hydrogen about that. So will marine life will be attracted or repelled? So it's a question you need to answer. So environmental noise. Will marine life will be attracted or repelled? How does it compare the existing impact of fishing and shipping fleet? That's a challenge. Collisions. Are the location and motion of wave energy devices obvious of marine life? Are the locations and motion of wave energy devices obvious to marine life? I'm not sure. Howling out. Can marine life like sea lions damage the wave energy devices? Of course. Yeah, they can go crazy if they are receiving electromagnetic signal, right? It can happen to anything. They can go mental and start pulling things out. So, howling out. Artificial reef effect. Will marine life congregate around the devices? How does the impact of local predator and prey relationships? So there are quite a few challenges, right? Now we know why people are not investing on wave energy much and others are doing. Right. Why wave power? Okay, I stop here. Okay, I want to take a break. Is it okay? I'll come back in about 20 minutes. Then we'll go for another 1 hour. Okay? That's fine. Thank you. I should have stopped this. Wave power. Are you guys ready? So we have been covering this for a while. Why different types of wave power, wave energy device. We slowly mentioned that, and I will give you more details as well as we progress. And when did we realize wave power? Why we need a wave power? When the people start realizing the wave power? Any idea?
All starting smashed up against blocks.
All right.
Surfing.
Sorry?
Surfing.
Surfing. Ah, yeah, this guy. Yeah, right. Yeah. I have a special site for you. Seriously, I have a special site exclusively for you. We said surfing, right? I have a slide exclusively for you towards the end. Hey, this is not working suddenly. Why? Any idea? When do they think about renewable energy? When they start thinking seriously? Huh? Oil peak, yeah, exactly. It all started in 1970s. Peak oil. When they start thinking about the peak oil, then come on. Okay, for time being, it doesn't like me. Off. Sorry guys, the computer got crashed. Yeah. So why peak oil? So why? Why? The reason is exactly it's oil peak. Because of the peak oil, people started investing in other technologies in 1975 or 1970s. Okay. So let's talk about a bit of history of wave energy and wave energy device. So it was first realized. The first patent came in 1799. The device designed on the ocean waves to generate power, and it's again belongs to the guys here in the first two row, always a proud Frenchman, right? Sorry. So first oscillating water column was built by, who's this? Berkshire Passaic. Exactly. That's why they started this like exactly like wind, and others adopted it. The French started it, Norwegian pioneered it. So it was started by French, first oscillating water column, and the power to his house. I'll show you the courtroom. In 1940, again Japanese experimented with the wave concepts with the submarine, and 2000 power. The wave power was delivered to an electric grid for the first time. Okay, that's a bit of history there. Okay, what was the wave power device in 19th century? So what is happening here is we saw the sinusoidal wave, we saw the oscillations. What happened when the oscillation is there? When the oscillating motion is transmitted to the pumps, okay, in the figure or other suitable energies, the figure shows that the float is there. We have a float here and moving up and down. So in an oscillation, and if you have a cog and the wheel there, the wheel is not visible actually, and the rods will move up and down. So what is happening is the mechanical oscillations. Mechanical oscillations just take place. This mechanical energy can be converted into electrical energy. Okay. So this is what exactly happening, and this is started even in the 1990s, but it wasn't progressed that far. Okay. So the realization of wave power device. This is what is happening. This is what happened in this guy French print. So as an early application of wave power device constructed in 1910s by Rouen Morex in France. So applied is house 1 kilowatt of light and power from a turbine. So he created a depth of few meters, and then he tunneled through the differential height. You know that last week we measured the low height and the high height, and how the pressure is affecting the energy and the storage. So that's what exactly happening. So he pumped the water column, put a shaft here, compressed the waves, and then this will oscillate again. This oscillation is converted back into the generators and get the power out of it. So that's a basic, very simple oscillation circuit. Okay. So to be more precise, that happened in 1910. In 1952, the oscillator wave column was further realized, making the wave energy device of oscillating water column have become rather popular since 1970s. And much earlier, 1952, the proposal shown here is nothing but the seawater enters. There is a hollow structure with both the lowered opening submerged. So what happened is you exactly have two blocks, and say for example these two are the blocks, and you force the waves to enter those two blocks. So that's what is happening due to the wave action inside the water column. So what happened is these waves of a different time period, maybe it is a swelling wave. So if you take the swelled wave, so shown in the water column, it goes into the upper column and the lower column, and the upper column is drained into the elevated water reservoir, and these water reservoir is again connected to another buoy, and you got the electricity from there. So it is one way of storage as well. Okay, the fixed device of water column. So this is what it is. So I've started now taking more on the device aspects, on the technology aspects. So we started with wave power, wave theory. We did something very little on wave theory as well, and then we saw the advantages and disadvantages, and then I'll go to wave devices. Okay, in the case of going back to this, so this is in the 1950s, and this is sometime in 1980s or 1990s, some sort of a cartoon picture. What is happening here inside? Okay, so once you start compressing the waves, once you compress the waves, it's happening. So the water level goes in, pushes the piston. Okay, pushes the piston here, and then air goes out, and that gives an enormous amount of energy, and you take it from here with the help of turbine, and get the electricity out of it. So it's air in, air out technique. So you can have a different different things. Once it falls and once the water rises and water lowers. So you can use both the oscillating pistons. Okay. No. Right. So oscillating water column, the partly submerged structure with the chamber having two openings. Air tapped in the chamber above the water structure is alternately pushed off and then drawn back into the chamber. So it's an oscillating motion. So it can push in and push back. Okay. The motion of air that drives, such as the Wells turbine, which generate electricity. That's what I mentioned a few minutes back. So these oscillate create enormous amount of energy. This enormous amount of turbine that generates electricity. So the Ebel turbine rotates in one direction regardless of the direction of flow of air. It's not flow of air, it's flow of air. Okay? Right. Who pioneered the energy devices? Okay, the energy devices were pioneered by Yoshimo Shida, Japanese Stephen Salter, and Gujal from Norway, Scotland, and Japanese. So they were pioneering the energy devices. Okay. So what is the Salter duct device? Okay, this is a sorry. Say again, sorry. No, I didn't get you.
They float.
The flow.
They float.
Float?
Yeah, they float obviously rather than submerge.
Somewhere, it has to be like that. It has to be like that. That's why the start. I will go back to show the real-time examples. Okay. So the wave entering. So you have a wave here. So this is the water level and the spine. So the wave entering from the left set the beak of the duct into oscillations. The back of the duct. So it's like this is the wave motion. So we are from the left to right slowly, and the back of the duct is circular to ensure no wave is propagated to the right. With very little energy transmitted or reflected, there is a very high conversion rate. So it starts pushing each other. So when it starts pushing each other, when waves start pushing the float, so the float is transmitting the energy with very high conversion over a broad and frequency band to match the conditions. So what happens is we have a conical flow, but the problem is you have to have exact calculations of how much energy it is going to get, how much energy you are going to get, and you have to place the float according to the calculated energy. So if the calculation is wrong, you are completely out. So the Salter duct design, even though it is a good design, that talks about the different, it is a good design. So in such a way that you get maximum potential by harnessing the wave at one end and taking the wave at the other end. Okay, so taking the energy at the other end. But the problem is if the calculation is wrong, it's completely screwed up, and it has happened. The Salter duct system failed many occasions because of wrong calculations. So originally envisaged came shaped bodies linked together along a flexible floating spine. The spine oriented towards the principal wave, making the duct a terminator. Okay, the scale of the duct is about 4.1 lambda. Benefits of duct design: can flip over and recover, of course, because it's a float. So the energy is more to flip over the other side, so it can flip on the other side as well. So where you get maximum potential energy, maximum kinetic energy, so it can flip over on one side and the other side. So you can always have the advantage of harnessing the energy when it is maximum. Okay, and mooring relatively straightforward due to flexible spine and more number of ducts oriented along the axis. So you can what you can do is you can also have a series of ducts fall over one side, other side, so that it varies according to the sinusoidal pattern. So you can, it's like tying a string of flags together. So when the air flows from one direction to another direction, you can clearly see the oscillations of the sine wave. So it is pretty much the same. The disadvantages: slow oscillatory motions, difficult to couple the electrical generators. That's one of the disadvantages. So advantages is also the same, disadvantage is the same. extracting energy from randomly rocking body because of different types of irregular wave patterns. Irregular wave patterns, so the extracting the energy is difficult. Okay, so the steps of waves energy conversion. So what you do exactly here is you input energy to a wave power device. That's what you are going to do. So what happened is the primary energy conversion, for instance, into energy in the pressurized air or water or a hydraulic air. So what you are doing is you are pressurizing those energy, primary energy for converting, and the secondary energy conversion by turbine. So you use turbine or hydraulic motor, and then you have a shaft, mechanical energy shaft will be rotating on other axis, and so the primary energy will be for converting the pressurized air and water in the hydraulic coil. So those are all in the rotating the main components. The other components is the motor, secondary, and the tertiary it goes to electrical generator. So you start with the boil, and then the pressurize the air. After that, you started converting the kinetic energy, which is generated into mechanical energy, and mechanical energy into electrical energy, and start transmitting the electrical energy. So this is the cycle. So steps for the wave generation. Okay. You guys are okay? And what is the paradox here? Paradox here is absorption of wave energy from the sea may be considered as a phenomena of wave interference. It's a paradox. So to absorb a wave means generate a wave. So you are absorbing something. So after that you have to generate. So to absorb a wave is to generate a wave. So otherwise, to destroy a wave is to create a wave. Right? To destroy a wave, you need to create a wave. So you want to store something. Right? Yeah, I want to store, but I want to store in a different way. So one wave is coming, another way. So I have to recreate more and more series. So that's a paradox. So what happens here is you consider a wall. Okay, the wave goes here, hits the wall, and turns back. So turns back and forth, 2 or 3 waves going like that. So the wave reflected from the fixed wall. Say remove the wall, the wave generation on the otherwise calm water due to wall oscillation. So this wall will oscillate according to the wave as well. So that wave is called generated wave. When you couple these two together, you will get an amplification effect. That is the generated wave. The result of incident wave is absorbed by moving wall because of the reflected wave is cancelled. So these two will cancel each other. The incoming wave and the reflected wave. So at particular time period, they will cancel out each other. And that will also give a resultant wave of the generator. Okay? So the other devices, so we saw salter duct device, and then what is that other one? Water. What is the other device we saw? By the French guys. Water oscillating, right? Water oscillating device. There you created the channel, right? For different pressures, and then the water starts oscillate from. You have air in and air out. So the water goes and pushes the turbine. I mean, we have a turbine that will generate electricity. Water comes down, so it oscillates up and down, right? So that we saw, and we saw the device. So there's another one is called the third device. Okay, this is Norwegian guys did. So the main body of the device floating on the surface, but moved to seabed via pump. As the waves propagate along the narrowing channel, so they constructed the channel here. So as the wave passes through the narrowing channel, the wave height increases due to shrinking of the lateral space. So you start confining the atoms or molecules. In theory, these are all again air molecules, water molecules. You start confining it, narrowing in the channel, and then you give a huge pressure. Even for the wave itself is coming with huge force and pressure. You again further create it by increasing the height and shrinking them laterally. When a wave crest is raised, so what happens is the wave is somewhere here oscillating, and then it goes up. It further rises. Okay, the wave crest is raised, to a level exceeding to the horizontal upper edge of the channel wall, the water from the crest spills the water from the crest into the elevated reservoir. So you make sure that the water goes with a heavy force, it spills, and take the generated electricity from there. Okay, that's the basic of the tether device. So this is what how the tether device looks like. So you have water coming up. They create a physical constraint. They can clearly see that due to tethering the horizontal channel, water is lifted to the reservoir 3 meters above. So the 3 meters above the sea level, the water in the reservoir flows back into the sea behind the reservoir dam on the turbine house to a conventional low pressure water turbine, and it's running around 300 kilowatt generator connected with local grid. What's your question, sir?
Could you use the reservoir that actually was going on there? Do you use the reservoir there like a dam?
Yeah, it's a dam.
Could you use it like a dam and produce electricity?
Yeah, exactly. It's a dam. It's a storage dam.
So they're increasing the head all the time, so they're trying to
Yeah.
squashing the
Squashing
water in, pours out the side.
Yeah.
And it's increasing.
And then they increase the height.
Yeah.
Yeah, so that the water falls freely from there. So use the dam. Now you know the idea. So they compressed. So the effect of squeezing the water. So the water comes from here. The water comes here. They squeeze the water along the channel, results in gaining the speed and the fury, giving an impressing view as the water drops to the walls and bursts into the reservoir. Okay. So
the generator is on the end of that.
End of that, yeah.
So that's the outlet of the channel.
Yeah.
No, that's the inlet.
No, this one is the inlet. That's right. Yeah. Sorry?
The reservoir.
Sorry?
The reservoir.
The reservoir is the outlet. There's a reservoir there, which is not shown. Okay, this is another device, oscillating wave power. So at load, the different designs, oscillating wave power has been realized for research and demonstration purposes. So it's again R&D. The picture shown here is the Japanese oscillating wave power. It's pretty much similar to what the French guys built in 1970s or 1910s or 1920s early. So OWC is tested in Zams in 1984. It had 2 well turbines, each of 40 kilowatt generator, in order to cancel the thrust force of the rotating shaft. So we are talking about the generating wave and the incident and the reflected wave. So they use these devices to cancel the effects so that they can maximize the energy. And the other one is circular calm. Okay, this is a different term. Circular calm. So what they have is they have around 12 to 15 types of interconnected chambers. So the chambers are there all around. So that you have a wave there, and again it's pretty much like it is less efficient when compared to the tether device. So because they are not forcing anything, but they are pretty much this will give less energy because of the we are not shrinking the energy. Whereas in the case of tether device, you are shrinking the energy, whereas here you are focusing the energy. So the 12 interconnect chambers arranged around the circumference. The chambers are interconnected and separated by the Wells turbines. The chamber is sealed against the seawater by a flexible reinforced membrane. So this reinforced membrane is the critical thing. So the movement of sea against the membrane. The movement of sea against the membrane. So you have a membrane inside here. The movement of the sea against the membrane forces the air. So this membrane, what happens is it acts as a barrier. So when there is a force, a heavy force comes that pushes the membrane through, and then it goes into the turbine and starts generating electricity. Okay, so they are using different compressing cylinders like this. There are about 12 interconnected chambers. So this is called circular charm, and it's there. If you are going to towards Scotland, Loch Ness or Inverness, close to that, it's there. Okay, and offshore devices again, Wave Dragon. So it's a new one. It's an overtopping device. So pretty much like what you are talking about, surfing board. So it's pretty much like a surfing board. So overtopping device which elevates when ocean level rises up above the sea level, and the water is let out through a number of turbines. So they have plenty of turbines around the overtop. So when it goes and oscillates, it will again start oscillating and generating the electricity, and you can take it out. So it's like a floating turbine. So the prototype is deployed in Denmark. The Bristol cylinder. So there are various there. I just picked only few. So other thing is Bristol cylinder. So this wave energy device was proposed by David Evans in the University of Bristol in response to incident wave submerged horizontal cylinder. So this is opposite to what we have saw in salter truck device and also the oscillating one. So with the sinusoidal wave, that combined oscillation results simply in a circular motion. So it started going in a circular motion whereby all incident energy may be absorbed, provided hydraulic power takeoff is able to provide optimum amplitude. So it depends more on, this device is more on the assumption that you have a more uniform calm sea. You have a rough sea, rough ocean, then this will not work. So this is an assumption because it depends on the uniform circular motion, and that all incident energy may be absorbed, but hydraulic power takeoff is able to provide optimum amplitude. So the amplitude should be realized and optimized. So the wave should be more or less with the error bar, it has to be more in phase. So the hydraulic power takeoff is built to the anchor. So you have an anchor here. So this has to rotate it has to absorb all the waves and rotate. Then after that, this will transmit to the turbine and get electricity. Finally, pitching raft. So the go green goes here. So finally, some shape it does. So a system called McCabe wave pump has been designed to produce drinking water or electricity by use of wave energy. So it has been developed by Dr. Peter McCabe and a team of engineers from Hydem Technologies Limited in Ireland. So the device makes use of this slope change on the water surface due to waves. A 40-meter long prototype was launched in Shannon, County Clare, Ireland in 1996. So that was close to about 2 decades now, right? So what happens is, so this device goes here, the water pumps the water, and then you have a hinge. These two hinges as a supporting for the shafts, and then you have a hydraulic pump. It pumps the water in, and then it goes into the turbine and gets in. So this is very simple device. And this device is there. You can see that this is what this device does. You can see that the flat bow pontoon and aft pontoon. So those two are here, and then you have an equipment cabin and hydraulic pumps. So that's the cabin, and the hydraulic pumps are here. And then again back to our offshore devices. Another one is Pelamis is a semi-submerged structure composed of cylindrical sections. You can see all the cylindrical sections. So we saw circular one, we saw the piston and bracken, and then now we are seeing a semi-cylindrical one. The wave induced motion in these joints, so the wave goes and it's induced motion in joints assisted by hydraulic ramps, which pump and high pressure oil through hydraulic motors and smoothing the accumulators. So the hydraulic motors, so we have a series of this. The hydraulic motors here that generates electricity. So it hits the circular cylinders, and in turn hits the hydraulic motors, and then the wave energy is converted into electrical energy. There is a video there in the YouTube here, so if you want you can click it and watch. So to give a brief recipe, you have a point observer, oscillating water column, overtopping, and attenuator. So all these things are what the brief slide which I've explained before. And oscillating water column, you know what happening in them. These are all different motion links in US and WaveGen in US as well. Again, wave attenuator with a different wave attenuator. As I said, you can clearly see that as the wave goes, you have a cylindrical portions here that hits, and then mechanical energy is converted into electrical energy. Perpendicular. Sorry? It couples in the lateral direction. So overtopping is a Danish wave dragon, the dragon which we saw. So what happens here is we have a imagine a hydroelectric plant, and the water reservoir is here. You compress everything here, and then these two are collectors, and then you have a wave energy converter. That's what it's exactly like. It's like this. So you turn this to 90 degrees and compress this, and there's a narrow gap here. You have an oscillation when the waves hits with the different oscillations. You start collecting the energy by different turbines. Okay. So we are coming nearly close to the end of the wave. So supply and predictions of wave energy is in 2007. European countries consumed about 2.9 terawatt of electricity. The ocean energy generates has a potential of 3.6 gigawatt of installed capacity by 2020. That's what the index says, and close to 188 gigawatt by 2015. This represents the 9 terawatt per year. At least they have to go by 2020, and this amounting 0.3 to 15% of EU 27 electricity demand by 2020 and 2050 respectively. So if you see that the trend, the offshore wind and onshore wind, offshore wind and ocean. So the trend prediction, this is coming from the European Energy Data Association. That's where I took it from. So 1990, and if you look at the trend is slightly favoring ocean as 2020. As I said, so in 50 years time, so we are now in 2011. So in 50 years time, probably that will go high. So that's what I said. It probably we may here to realize or if there is anything. Okay. So the wave energy target for Ireland 2020 is 0.5 gigawatt. Did I say kilowatt or megawatt? Right? I said megawatt. So, yeah, it's 0.5 gigawatt. That's the target for Ireland, and France is 0.8, Spain 0.1, Portugal 0.3, Denmark 0.5. In UK, it's slightly optimistic, it's about 2 gigawatt. So economics, so reducing the operation and maintenance cost is key to successful economic implementation of wave energy station. Capital cost per kilowatt of wave energy estimated to be double that of fossil fuel installations. Load factor is average power divided by peak power. That is what load factor is, right? We have saw the efficiency and capacity factor, right? So the load factor is average power divided by peak power, lower than the conventional due to variability of wave climate. Wave energy cost can only be competitive if running costs are significantly lower than the conventional station. So that takes a huge hit, right? The running cost is huge, maintenance cost is huge. So those are all the challenges. The fuel costs are zero, therefore, so you don't need a fuel, right? That's an advantage. You don't need a fuel, you don't need oil, you don't need sun. Of course, you need sun to deliver, right? But there's any physical fuel is not there required. So the maintenance costs are determined by the other factors. Okay. Finally, the tsunamis or giant shallow water waves. So there is a huge problem as well. So because of tsunami, giant shallow water waves. This one is devastating. There's the Lisbon one, 1755, is already suffering a past spreading fires caused by the earthquake and trigger wave. So most of the city population has been completely destroyed. So waves are also dangerous. And the other slide, other cartoon which I have is exclusively for a French guy. And the saw of the surfing board. Can we do by surfing board? That's what you asked, right? Imagination. Exactly. So sorry?
It's electrocuted.
Yeah. So my first slide, I showed something like this. If you remember, a wave with a bulb, and probably, so pretty sure you won't be doing this in your holidays, right? Okay? Right. So we have still some more time. I would like to take the geothermal session. Is it okay? Right. That's geothermal energy. So everything is under the land. Right? Everything is under the land. That's what geothermal. Right. So geothermal energy require increased use of indigenous. Okay. Where we stand in geothermal energy? Any idea? Is it feasible?
Only in certain places.
Sorry?
It's only in certain places.
7 places. 5.
Cruisers.
Mm-hmm.
You don't have a high temperature close up surface, so your thermal efficiency is going to be very low.
Mm-hmm.
Compared to the amount of energy that you invest to get down there to reach this. So for someone on Iceland, it's no problem.
Sorry?
If you're someone on Iceland, it's huge. Here, about 70 degrees, you get down maybe 3 kilometers, but something more moderate.
Sure. I agree with you. Any other?
There's a big enough surface area of coil underneath the ground. If you're able to have some mechanism to, you can cope with a low temperature difference between the source and the sink. If you have a large enough surface area that's kind of transmitting the heat transfer across something like a big version of the heat exchanger.
Mm-hmm. Yeah, I can accept that, yeah.
I think the earth is going to be better than the water.
Sorry?
The earth is going to be better than the water. It's so faster.
Yeah, exactly. No? It does. Sometimes you know, right? Any other? Yeah, so the guys are almost right. So I would say 2 types of happening. So there requires increased use of indigenous renewable energy sources. There are 2 fundamental sources of renewable energy. The sun, solar, right? The sun is looking outward. I would say Earth is looking inward. So sun is giving the rays to Earth, right? Am I correct in saying that? Yeah. And the Earth receives. So you look inwards in the Earth and what's happening here. So how much energy it receives and how it can consume the energy, how it can release the energy. So it's an inward one. Okay. Currently we are focused. All our energy was currently focused on the outward for solution. Right? The outward is the sun. We are not more on inward. The outward is what? Photovoltaic, solar, wind, water, wave. It's all outward. Right? Because it's outward energy. So currently we are looking for an outward for a solution. Example PV, concentrated solar panels, bio, wind, etc. Looking inward. So that is the difference between geothermal and others. Because those are all outward and this is inward. So geothermal is thermal energy which requires improved technology and understanding of subsurface environments. So it's an improved technology. We need more technological advancements to realize this. Okay, let's talk about this. Okay, so this is Earth. So we have an Earth with an inner core, outer core, lower mantle, transition zone, upper zone, and the crust. So there's a huge difference from 0, 15 degrees, 1000 degrees. So we have to reach the core to get the more temperature. That's another difficulties. Okay, so quickly go to the background. The temperature in the interior of the Earth is about 4000 degrees. So somewhere here in the interior, right, close to the core. It's about 4000 degrees. Sorry, it's about 4000 degrees. The heat flows out from the mantle and crust of the Earth with average temperature gradient of about 30 degrees Celsius per kilometer. So it's quite a lot. That's quite a lot, 30 degrees per kilometer. The heat flows out from the mantle and crust. So you have a mantle here, upper mantle, lower mantle to the crust. So that's where it is. So the heat flows from mantle to the crust at an average of 30 degrees per second. The heat flow is maintained by radioactive isotopes, heavy nuclei, and cooling of core and mantle. So you have this. The natural occurring stem jets, that geysers and hot springs up to 35 degrees Celsius provide a ready source for thermal energy. So the geysers and they're all acting as a source or the hot springs, right? So in more geologically stable regions, thermal energy can be extracted by drilling boreholes and depths of few kilometers. As Paul rightly said, there's a difference between doing that in Iceland and Antarctica, right? So that's what it is. In more geologically stable region, geothermal energy can be extracted by drilling holes to depths few kilometers and flushing water through hot rock formations. Heat extraction can be achieved through an aquifer, described next in the section, or a hot dry rock system where water is passed through narrow passages through natural fissures. So do you know anything about aquifer? Any idea?
Take the heat out of the liquid, isn't it?
Sorry?
It's to take the heat out of the liquid. It's already moved.
Yeah, aqueous water, right? So heat out of the liquid.
And that first is basically the water table underneath the ground, underneath the bedrock.
Sorry?
That first is basically the water table.
Water underneath the bedrock.
Water table.
Water table underneath the bedrock. Could be. Try. Right. An aquifer is a layer of porous rock. Okay? It's a layer of porous rock. It's a layer of impermeable rock as well. Okay? And aquifer of depths 2 to 3 kilometers away are typically 60 to 90 degrees Celsius. So you have both cold front and the hot water here. Hot water and the cold water. It's like a you can imagine vaguely of our Carnot engine, right? With one side adiabatic expansion, other side is isothermal expansion. So because of the cold and the warm and the different pressure and the temperatures. Okay, so it's pretty much similar. So the cold water is injected. The cold water you get is injected at some point into the aquifer through a borehole. The water flows through the aquifer and absorbs the rocks, absorbs the heat from the porous rocks, and then the water is removed from the second bore, okay, from the hot bore. So this is what exactly is happening. An aquifer is a layer of porous rocks and a layer of impermeable rock. Aquifer has a depth of about 2 to 3 kilometers, typically at about 60 to 90 degrees. It's an important thing to remember. Okay, this aquifer is important to remember how you extract heat from the aquifer. So you pour cold water into the aquifer through a borehole. The water flows through the rocks, absorbs it at the V is equal to Vf, and then by the specific length, and then you take it out from the second. Okay, the system power output, the cold water is injected into the system at x is equal to 0. So say for example x is equal to 0 here, you inject the cold water and extract it at the specific length L. Suppose the aquifer is initially at temperature T1 and the cold water is at temperature T0, then the heat available per unit volume, I think it's a differential temperature delta T with respect to specific heat volume. So assuming the volume of the flow rate from the water is Q, then the power output is a combination of differential temperature and volume and also the density as a function of density. Okay, this is a simple equation which we know. Okay, so the velocity of the cold front, let the cold front move from a distance delta x. So this is the cold front here. If the cold front moves a distance delta x like this up to here or whatever it is, delta x in time c, then the fraction phi is the volume occupied by the pores of known porosity is given by delta phi is equal to 1 minus phi dA times. So these are all the equations. The amount of heat removed from the elemental volume. So you have, once you get the heat, you have to remove the heat. It is a function of differential temperature and as a function of differential volume with respect to area and delta x. So the volume of water passing through that element is given by the ratio of the flow and the delta T. The heat gained per unit volume is again delta T times specific heat capacity. Then you do what you have to do is you have to work on the energy conversion from the heat loss to the heat gain. So that is what this equation is. So the velocity is a function of dx by dt, which is nothing but as a function of both inlet and the outrun densities in the waters as a function of velocity of the flow. Okay. The lifetime of the system is the time taken for the cold front to reach the outlet of the bore. That's what defines the lifetime of the aquifer. So T life is equal to L by Vf, which is 1 minus 5 by the differential ratios. The total amount of the available thermal energy of the system is again the ratio of the different densities and the temperatures. The choice of the volume and the lifetime is a position. So it's all depend on how whether the delta x is different or X is different. It depends on the, we know that it depends on the flow rate, and it depends on the differential temperature, and it depends on the position. So determine whether these are all determines the economics of the system. So finally, geothermal law of economics. First law, completed well cost increases exponentially with depth. Second law, power plant cost decreases linearly with temperatures. Third law, as the source quality decreases, the drilling cost dominates. Okay, first law is completed well cost increases exponentially with depth. That's right. Power plant cost decreases linearly with temperature. Okay, and third law is as the source quality decreases, the drilling cost so dominates. So these are all more obvious points. Any comments on this? No? Finally, must save, must cost. Must solve the problem. How are you going to reduce this to here and to $8? That's what the cost analysis is. Okay? So that's where I am. Today's class is over. Thank you very much, guys.